All right, hello everyone. Today will be the last lecture, so we'll finish this up. We'll get the homework questions done, and that'll give you time to complete your exams. So I enjoyed teaching everyone. Please remember to fill out the surveys. So we left off on slide 62, so let's go to slide 63. They talk about conjugate addition reactions. It says, recall that the alpha beta unsaturated carbonyls are made by aldol condensation, and they show you the alpha beta positions. Let me see my textbook too. Alpha beta unsaturated carbonyls have 3 resonance contributors. Let's go to this in our text. Always a good idea to follow along in the textbook. You can see an aldol addition on page 970. Let me see, 21.6 though. All right. So there. So 21.6 starts on page 986. They talk about this alpha beta unsaturated have 3 resonance contributors, and they show you the contributors right here, 1, 2, and 3. It says the beta carbon and the carbonyl carbon are electrophilic. That means they'll accept electrons. And you can see this on page 986 where it says 2 electrophilic positions. It says both of these positions are therefore subject to attack by a nucleophile, and the nature of the nucleophile determines which position is attacked. And then they go an example of a Grignard reagent on this next slide. So this is called a 1,2 addition. Let's see. This one right here, and you put it right here, it's a 1,2 addition. Gilman reagents generally attack at the beta position. So remember, this is the alpha, this is the beta position, and this is the 1,4 addition. And they go over a general mechanism for the conjugate addition right here, where the nucleophile, if it attacks at this beta position, then we have an enolate followed by an enol. The enol then tautomerizes to the aldehyde ketone. And notice that it wants to mainly stay in this position right here. Obviously, there'd be a proton transfer. So stronger nucleophiles tend towards the 1,2 addition. Less reactive nucleophiles tend to do the conjugate addition. Typical enolates often give a mixture of the 1,2 and the 1,4 addition products. Stabilized enolates give the 1,4 addition exclusively. So let me see. And then, which leads into this Michael reaction. So stabilized enolates give the 1,4 addition exclusively. This conjugate 1,4 addition is called a Michael reaction. A Michael donor is a nucleophile that does conjugate addition. A Michael acceptor is equal to the alpha beta unsaturated carbonyl. And let's see what they say about this. It says, in contrast, doubly stabilized enolates are sufficiently stabilized to reduce the 1,4 conjugate addition exclusively. Where they talk about the Michael donor, they're not showing this, but the Michael donor, we can show this. Here'd be your Michael donor. There's an electron right there, and then the Michael acceptor. That's a partial positive right there. And then they give a variety of Michael donors and acceptors on the next slide. And they go into this Stork enamine synthesis. It says because singly stabilized enolates do not give high yielding Michael additions, Gilbert and Stork develop a synthesis using an enamine intermediate. It says recall how an enamine is made, where you have a Michael donor. So they show you the enolate ion, but an enamine is less nucleophilic and is a Michael donor. You can see this right here, where this would be a Michael donor. And then it would find a Michael acceptor. And there'd be some electrons here. And they show that really good example of this on the next slide. We have the Michael donor going to the Michael acceptor. We have movement of electrons. So after a conjugate addition, aqueous acid converts both groups into carbonyl groups. So there's 3 steps to this. You have the formation of the enamine, the Michael addition, and then hydrolysis to get your ketones. And then this chapter talks briefly about the Robinson annulation on page 992. They don't talk about it too much. They just say, in this chapter, we've seen many reactions. When performed in combination, they can be very versatile. It says one such method for forming a ring in which a Michael addition is followed by an intramolecular aldol condensation. And they say this 2-step method is called a Robinson annulation. And you can see this right here. Then they go over some synthesis strategies. We'll see this in our homework today. So Stork enamine synthesis are for 1,5 dicarbonyl compounds. Aldol and Claisen are for 1,3 difunctional compounds, and they give some examples. So we've learned 2 methods of alkylation. The alpha position of enolate attacks an alkyl halide. A Michael donor attacks the beta position of a Michael acceptor. Here's an example of alpha halogenation. Show that here. Aldol addition and condensation. Cross aldol condensation. This is stuff we'll see in the homework. Claisen condensation. This is stuff we talked about. Alkylation by enolate. We talked about the Michael addition. The Robinson annulation was just what, and that's it. So we'll go on to the homework. We won't take that much of a break. Just give me a few minutes to open it up. Right, we're resuming recording now. We are gonna get the chapter 21 homework problems done. There's not too many of them, there's just 13. We'll start with question 1. It says addition of water to an alkyne gives a ketoenol tautomer. Product, draw an enol that is in equilibrium with the given ketone. So we'll go ahead and do that. This is question 1. So that's the enol. They show you the ketone. I won't draw that because I don't want to confuse anyone, but you want to have it in the enol form. All right, let's go on to question 2. We can do question 2 on the same slide. Well, let's use a different slide. It says draw the curved arrows for the formation of the keto form. So we have, for step 1, we have this compound. We have a base. That base is going to take a proton. I'll put the electrons in right here. Let's trying to do this the best I can. We're putting it on that corner right there. So we're going to be in equilibrium. Got our ketone. Now we have our carbanion. Let me see. These electrons will come. Well, I think they want charges. Yeah, they do. So we have a negative charge here. No. Comes here. We'll move the electrons onto the oxygen. Then we finally have this. So this was step 2, step 1, and step 3. That's it. That's question 2. I forgot this right here. Sorry. Forgot the double bond there on 3. So we're going to be kind of doing the same thing on question 3. It wants both the enolates. Okay, so let's go to question 3. So question 3, they show us this compound here. They show us this, a 6-membered ring. Ketone. So you have a proton here and you have a proton here. So that base can either take it from this side or the base can take it from this side. So depending on what side you're taking it from, you're going to form either or enolate. So if we take it from this side, just an arrow, we'll form this. If we take it from that side, we're going to form this compound. Double bond there. All right, so let's go to question 4. Question 4, it's pretty easy. It's just gonna be we're just gonna add a bromine group to it. Um, it's an acid catalyzed bromination. So we have this compound, benzene, and have this. What we're going to do is we're going to add a bromine to this position right here. I want to just put an arrow here, and we're going to add a bromine here. And that's all we did. Oh, I did forget to put this methyl group here. And we can put question 5 on the same slide. 5, we have the haloform reaction. Let's see. So this compound, our benzyl group here, our ketone. At first, this has all hydrogens, but under the conditions, we're going to add chlorines to it like this, right? This ain't the final answer. But then what happens is that this becomes a really good leaving group. You have this coming in like this. This will be gone. So you can just imagine, one of your products is going to be this right here. Well, the second product will be the acid. So this is benzoic acid. So this is what you're going to get for your 2 products. Let's go to 6 then. 6 is an aldol addition. That's the title of the question. So we know we're going to have an aldol addition. Let me see. So we're starting with this compound here. We do have a base. So that's going to take a proton here. The electrons are going to move here. And once we have this, it's not the final answer, but we have these. We have a carbanion. We still have the same compound out there, right? This is just another one of these compounds here, where we can target the ketone group. And then these electrons will be pushed here. And once those electrons are pushed there, we have something like and this will add a proton from water. So I'm going to put a H here. I think that's it. So remember, this will be a proton transfer, H2O. All right, let's go on to 7. The 7 says, draw the structure of the product form when the given compound is heated in aqueous solution. They give us the compound. So we have this compound. Let me see. So given that, we have some hydrogens here, right? We do have a base. Sodium hydroxide is a strong base. So if we take that one, move the electrons here, these would come up here. This would come here. This could do an attack here. 1, 2, 3. A 5-membered ring. We see we create this 5-membered ring. It can be protonated with water, so I'll just draw the OH there. We do have a hydrogen here. We could protonate it again. Oh. Now if we protonate it again, it's going to become a really good leaving group. This OH. We'll be left with our final answer then. We only have 8 carbons, 1 oxygen, and 12 hydrogens. So that's 7. This is number 1 here. Let's not confuse anyone. So question 8, we're gonna go into a Claisen condensation of ethyl propanoate. We just have to draw a bunch of curved arrows. So let's go on to 8. So there's a bunch of different steps here. There's an R group coming off of this. We'll come back to it if we need to. First thing is it's going to take a proton here. The electrons are going to move. It's going to be in equilibrium. Step 2 then. And we're going to use a different thing for. We have this. It's going to come back here. If it does that, we have another one of these things. These electrons can attack here. So it'd be coming from this carbon right here that you're going to attack right down at the ketone. And that leads me to step 4, which I'm going to put this on another slide. These electrons come here, and this bond will be released to here. So that's gone. So now we're on to step 5. Now we're going to take the leaving group. I can grab a proton. This brings us step 6. Oxygen anion. If we reform the ketone again, we have HCl in here. It's going to be a proton transfer. And then they want the final product, so this will be 7. All right, so this is the final products. All right, so let's go on to 9. 9 has 2 parts to it. It says comparing clays and aldol products. They give us 2 reactions. Let's draw the most stable one. 2. So there's a hydrogen sticking off there, right? And then we have a base. Take this, jump there. What's going to happen is then we're going to have an electron movement. This will come, and then this is going to go and attack. And it'll attack at the ketone group. So there's another one of these out here, right? So if I just show it attacking right here, that's where it's going to attack at. So let's draw that then. And then this, you have electrons that can come down here and this will be released. So then we'll have our final product. I guess this is 9 part 1. We won't be able to do all this on this. Then there will be a base. This base, there'll be a base that takes off this proton here. And these electrons will form a carbanion. So I'm not going to redraw the whole thing. Let's put these electrons here. If we put those electrons there, then this would be negative charge here. There we go. And we can do B here. Likewise with B, we're going to do the same thing. You know, with B, I'll show you the answer, but where you're going to do your first base attack, you have this right here. That base is going to take a proton here. It's going to come here, and then it's going to do what we did with the second one. So if we follow the same steps, we're going to end up with this. This is the second part of the answer. This is part B, and this one is part A. All right, so let's go on to question 10. A US 1 phenylethanone that's has a ketone. LDA is a strong base. Then they're going to give us a second reaction. So we have to see where we're going to pull the proton off of. Let me see. Proton here. LDA is a strong base. So we have a base. Pull that proton off. Wait, I should have drawn a methyl group. Put the proton off. So then if we have, I'm just going to draw a phenyl group like that. So I'll draw the final answer. So we have this phenyl group. We have our carbon linkages, and then we have the other phenyl group. Like that. So this is like an SN2 reaction. Or we have a good leaving group. It's a conservative reaction. And that's it. You just draw this. So let's go to 11. This is predict the major organic product of the given reaction and complete its mechanism. So why don't we just go ahead and draw the curved arrows first, and then we'll give the final product. They'll help us get there. So, and this is basically an R group. So we have a base. Electrons will pull here, come here, come here. We're going to go left to right. And all after this is just an R group. So this will come here. Then this is going to attack. Where will this attack at? Let's see. Oh yeah, they have chlorine in that one group, right? So just like we did before, chlorine's going to be a good leaving group. So let's try to attack a carbon. That chlorine's going to be a good leaving group, and it's going to go. And you have all that other stuff coming off. So what we're left with, no. That's not all I want. So you have all this. You gotta make sure you put your lone pairs of electrons on. Plus Cl minus. Now they want us to draw more curved arrows. Okay. So this is Go lone pair of electrons here. It's going to grab that proton. When it grabs that proton, this bond is going to move here. And we're going to have a bond move here. So one of the products is going to be CO2. You see this right here? So we're going to get CO2, and that's going to come off as a gas. The other product, we're going to have, we have this stuff right here, right? This, when that did that, let me see something. I forgot one arrow. I forgot this arrow. This will push these electrons back on that oxygen. So step one of the process kind of revolves grabbing the proton. This proton, then the bond between the hydrogen and the oxygen moves to make CO2. This carbon-carbon bond is released. When that's released, this keto group is going to release its electrons to the oxygen. So we have CO2 plus we have this now, right? We have this. Everything else is going to stay the same. What's going to happen here? This is going to lose its double bond. It's going to be protonated. So these electrons are going to come down here. This is going to grab a hydrogen. So what I'm going to do is draw the final product. So we're going to have a keto group right here. We're going to get rid of that double bond because it's going to grab a proton. And it's going to grab a proton because we have acid in there. So this should be your final product then. You get CO2 plus this. Usually we take a break, but we're going to go right through it. We only have a couple questions left. I'll let you finish this up, and I'm going to read question 12 to myself. Okay, let's go to question 12. Remember, I'll be posting all this, so you'll have all this. Just draw the structure of organic product form when the compounds undergo the three-step reaction sequence indicated. We have this. We have a strong base in there. If that takes that proton, then we'll form a carbanion here. So then what I'm going to do is just draw this stuff here. This carbanion. Let's show it like that. Got all this. And then we have a good leaving group, don't we? We have, I'll try to show it. But this bromine group here, you can only imagine that. We're going to attack here through an SN2. That'll be a good leaving group. And let's bring this up here, actually. There you go, we have a 6-member ring there. It's a little complicated here. Then we take this hydroxide, and this ester group is going to go. Got a 6-membered ring here. Eventually this would be here. This will come back down. We'll end up with this. If this grabs here, this will come here. This will be released here. Here's your CO2 being released. And you got CO2. If that bond takes this can come here, and we'll be left with we're running out of room, so let's start write it right here. Come up here. And that's it. So this is the final product they're looking for in 12. All right. So let's go on to the final question. Question 13. This is just going to be arrow pushing. Let's complete the curved arrow pushing mechanism for the microconjugate addition reaction. Add the missing bonds, non-bonding electron pairs, and curved arrows as needed. So it wants us to add it all. So they show us ketone, show us acetone, minus here, take this proton here, put this right here. Now we have this carbanion. Well, they're showing it on the other side, so I'm also just keep it the same. It's not letting me delete this. For some reason it won't let me delete that. That's okay. There it goes. So I can push these electrons here. I can push those there. And the last step will just be the protonation. Let me see. So we have the final product. Got our benzene ring. Got this. Coming up, we still have our aldehyde. Nothing changed there. I guess they don't want, they want, sorry about that. The aldehyde, we have these electrons here. That'll be protonated. That's it. So once that's protonated, you could draw the final product. I think they show the final product, so that's it. So that's the Michael conjugate addition reaction. All right, that's all 13 questions solved. I hope you had a great day. This is it. So there'll be no more lectures after today. So just make sure you get your homework done, make sure you get your exam done, and you should be good to go. So if you have any questions, I'll stay back and answer any questions. Other than that, you're free to go. Have a great day.